In this video, I'll talk about reversible reactions and chemical equilibrium. If the reaction from A to B and the reaction from B to A take place at the same time, we put a double arrow between A and B, we say it's a reversible reaction. Actually, it's not just one reaction, it's two reactions. And we say it's a reaction mechanism more accurately. A reversible reaction will eventually reach equilibrium when the forward reaction rate is equal to the reverse reaction rate. So let's assume this is a first order reaction from A to B with a rate constant K sub F. The forward reaction rate is K sub F times the concentration of A. And then let's say, well, this B to A is also second order. The reaction rate from B to A is K sub R times B, because in this step, B is the reactant. Therefore, when this Kf times A equals Kr times B, the forward reaction rate equals the reverse reaction rate. And then let's look at this equilibrium video.
A chemical reaction at constant temperature in a closed system is in a state of dynamic equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. Dynamic means the reaction occurs in both directions. Equilibrium means there are constant concentrations of both reactants and products in the system. Consider a wet towel hung out on a line. High-energy water molecules can evaporate and are removed in the breeze. This continues until the towel is dry and can be represented by a simple chemical equation. This is an open system. If the wet towel is left in a closed sports bag, it does not dry. High-energy water molecules evaporate and remain as vapor trapped in the atmosphere around the towel. At the same time, low-energy vapor molecules condense on the surface of the towel to a liquid. The rate of evaporation exceeds the rate of condensation until the vapor becomes saturated. At this point, a balance is reached where the rate of evaporation equals the rate of condensation. A state of dynamic equilibrium is reached, represented by a double-headed arrow. Dynamic equilibrium only occurs in closed systems.
All right, let's get back to the document. Again, at equilibrium, both reactions are taking place. A is converted to B, and B is converted to A. However, the rate of the forward reaction is equal to the reverse reaction rate. And therefore, we observe no net change of the concentration of A or B. Well, if Kf times A is greater than Kr times B, then overall the reaction is moving forward, A is consumed, B is produced. If Kf times A is less than Kr times B, that means overall the reaction is moving backward. B is consumed and A is produced. Again, just to emphasize, the chemical equilibrium is a dynamic equilibrium. At this dynamic equilibrium, both the forward and reverse reactions are taking place. However, there's no net change of the concentrations of A or B, only because the forward reaction rate is exactly equal to the reverse reaction rate. Now let's work on one practice problem. For this A and B reverse reaction. Again, pay attention to this double arrow between A and B. The initial concentration of A and B are 1.0 molar and exactly 0 molar for B. What are the concentrations of A and B after this reaction reaches equilibrium? What are the forward and reverse reaction rates at equilibrium? So you're given the initial concentrations of A and B. There's no B in the system at the beginning. There's 1.0 molar of A. And then you're given the forward reaction rate and the forward reaction rate constant and the reverse reaction rate constant. And then we need to answer these two questions. First, I want to remind you, if you consume 1A, you will get 1B, right? So if you consume 1 molar A, you will produce 1 molar B in the same reaction container. I'm assuming A and B are occupying the same reaction container. Therefore, the volume is the same for A and B. All right. So again, if you consume 1 mole of A, you will produce 1 mole of B. And because A and B are occupying the same reaction container, we say if you consume 1 molar of A, you'll get 1 molar of B. If you consume 0.2 molar of A, you will get 0.2 molar of B. Right? So because again, if we pay attention to the coefficients in front of A and B, there is a 1-to-1 ratio. So my point is this. The sum of the concentrations of A and B never changes during the reaction. So at the beginning of the reaction, the sum is 1.0, and then throughout the entire reaction period, the sum of the concentrations of A and B should always be 1.0 molar, right? So again, you can imagine you are giving money to a friend and the friend is giving money back to you. And no matter how much money you give to your friend or how much money your friend is giving to you at whatever rate, in the end, I believe the sum, the total amount of money between you and your friend is a constant. All right, now let's work on this problem. Again, I hope I convinced you this A plus B is a constant throughout the entire reaction period. And therefore, A plus B is equal to the initial sum of A and B. And initially, A is 1.0, B is 0. Therefore, the initial sum is 1.0. Therefore, the sum of the concentrations of A and B remains unchanged. It's a constant 1.0 molar. But we have only one equation right now with two variables, A and B. So we need another equation. At equilibrium, we know the forward reaction rate is equal to the reverse reaction rate. So this is the forward reaction rate, Kf times A. The reverse reaction rate is Kr times B. Now we have another equation. We set A to be X. This is just for convenience. And then we have forward reaction rate times A over here equals reverse reaction rate times B. What's the concentration of B? By using this equation, we know the concentration of B is always 1.0 minus the concentration of A. And therefore, we have 1.0 minus X here. All right, so what is this 1 and 4? They are actually the reaction rate constants, the forward reaction rate constant and the reverse reaction rate constant. How about units? Anyway, the units are the same, therefore they cancel. Okay, so let's solve this equation. It's a simple linear equation that contains only one variable. So really it's just x equals 4 minus 4x, therefore 5x equals 4, x is 0.8, and then we have the equilibrium concentration of A is 0.8 molar. Alright, so I forgot to add this at equilibrium. This is very important because the concentration of A actually changes. At the dynamic equilibrium, it does not change anymore. So what's the concentration of B at equilibrium? It's 1.0 minus 0.8. It's going to be 0.2 molar. Now we're going to compute the forward and reaction rate given these two numbers. All right. So the forward reaction rate is the rate constant. It's 1 times the concentration of A at equilibrium. The result is 0.8. How about the reverse reaction rate? We need the rate constant, which is 4 per second, times the concentration of B. And then the result is also 0.8. It's not surprising because, again, at equilibrium, the forward rate should be equal to the reverse reaction rate. And at this point, there's no net change of the concentrations of A or B.